Hello, I'm Wei-Chen from the University of Bristol in the UK. I'll be talking about our recent study on measuring the maturity of SYCL implementations by tracking historical performance improvements. SYCL is a platform-agnostic, single-source C++-based parallel programming framework for developing platform-independent software for heterogeneous systems. As an emergent framework, SYCL has been under active development for several years, with multiple implementations available from hardware vendors and others. A crucial metric for potential adopters is how mature these implementations are. Are they still improving rapidly, indicating that the space is still immature, or has the performance improvement plateaued, potentially indicating a mature market? This study presents a historical study of the performance delivered by all major SYCL implementations on a range of supported platforms. We use existing HPC-style mini-apps written in SYCL and benchmark these on current and historical revisions of each SYCL implementation, revealing the rate of change of performance improvements over time. Additionally, we also compare the most recent SYCL performance to existing well-established frameworks. Here, both OpenMP, OpenCL, and CUDA are all C99-derived frameworks that require direct compiler support, whereas Cocos is a C++-derived framework that is implemented as a library with no specific compiler requirements, although the appropriate runtime is still required. We adopted the three main actively developed SYCL implementations for this study. Let's briefly go through each of them. First, ComputeCpp is Codeplay's proprietary LLVM-derived SYCL conformal implementation. It is one of the earliest SYCL implementations. Codeplay started development of a prototype SYCL implementation, SYCLcon, as early as 2014. SYCLcon left prototype stage around Q4 2015 and was renamed to ComputeCpp with commercial support. The implementation makes use of Intel's OpenCL runtime, along with a now deprecated CUDA backend as shown in the support matrix table. And we have Dpc Plus, Intel's fork of LLVM, which adds language-level SYCL support. Similar to ComputeCpp, Dpc Plus requires Intel's own CPU and GPU OpenCL runtime and follows the same execution model. Dpc Plus has been under heavy development since Q1 2019. Beginning from December 2020, the Dpc Plus compiler has reached the production-ready stage and has been shipped as part of one API. Finally, SYCL is an open-source implementation of SYCL based on LLVM that supports multiple backends. This project is led by Axel L-Pei from the University of Heidelberg. For CPUs, SYCL directly translates to OpenMP, thus being able to take advantage of all existing LLVM optimizations on this front. For GPUs, SYCL acts as a wrapper for SYCL function calls, which abstracts on top of vendor-specific frameworks such as CUDA or IMP. An experimental Level 0 and Intel OpenCL backend is also being developed. We undertake a historical study evaluating the performance of our benchmarks through time as each SYCL implementation was developed. For closed-source compilers like ComputeCpp, we collect all publicly available releases from vendors' website. For open-source compilers like OneAPI and SYCL, we download nightlies if available or compile from source directly. Revisions are selected based on the rough interval, with adjustments for interesting-looking commits. The platform matrix gives an overview of the status of the platform support for each of the SYCL implementation. Solid circle indicates full support, half circle indicates partial support, and hollow circle indicates no support. This study will only select platforms where full support is available. For benchmark hardware, we select devices that are directly supported by our SYCL implementations in the previous slide. For CPU devices, we have selected commonly used HPC CPUs from both Intel and AMD. Both the Intel Xeon CPU and AMD Zen 2 CPU are installed in a dual-socket configuration. We utilize all available processors during our benchmark with the most performance scheduling and affinity options. For GPU devices, we are constrained by what the SYCL implementations have support for. NVIDIA's V100 GPU was selected for its support in SYCL. Both Dpc Plus and ComputeCpp have experimental support for NVIDIA devices, but only the very recent versions of both compilers with varying levels of completeness. Both Dpc Plus and ComputeCpp have experimental support for NVIDIA devices, but only very recent releases for both compilers and with varying level of completeness. Because of this, we have decided to only include NVIDIA GPUs for SYCL at this time, hoping to add the others in a future version of this study. To allow comparison between Dpc Plus and Compute CPP on the GPU front, we have selected Intel's P630 iGPU. This particular iGPU is part of a Xeon CPU, which is representative of typical HPC and data center use cases. Note that we'll be comparing our results to the theoretical attainable performances on each device. For example, for compute-bound benchmarks, we calculate the achieved arithmetic intensity as a percentage of column on the furthest right. We will not be comparing performances between each devices as this isn't the focus of the study. Our first mini-app is the memory bandwidth-bound benchmark called BabelStream. BabelStream is a port of the standard stream memory benchmark. It is implemented in a wide range of parallel programming frameworks, including SYCL. The benchmark implements 5 memory bandwidth-bound kernels: copy, multiply, add, triad, and dot. These kernels have very light compute requirements, and it is expected that most parallel programming frameworks should be able to attain high percentages of the theoretical peak memory bandwidth of the underlying hardware. The SYCL implementation contains around 300 lines of kernel code. The implementation lets the runtime choose the optimal workgroup size. For this study, we will only be looking at the triad kernel as shown in algorithm 1. It is widely regarded as the most representative of real-world behavior, requiring 2 loads and 1 store per data item that it processes. Here we present results of the memory bandwidth-bound BabelStream mini-app. Compute CPP results are shown on the bottom left chart. It achieved a relatively consistent runtime for all versions, with a significant jump in performance on July 2019 from version 1.1.4 onwards. The release notes during that time only mentioned bug fixes. Given the reliance on Intel's own CL runtime, it is interesting to see comparatively lower bandwidth achieved on both Intel CPUs and GPUs compared to AMD CPUs prior to the step change in July 2019. The difference mostly disappeared on version 1.1.4. We also observe both Intel and AMD CPU results here only achieving half of what the Intel GPU is getting. The Dpc Plus results are shown on the bottom center chart. Results for all platforms have remained remarkably consistent during Dpc Plus lifetime. Here, Intel GPU runs consistently, achieving nearly 80% of the peak memory bandwidth, while both the Intel and AMD CPU results are closer to 40%. Note that the lower bandwidth observed here are consistent with larger problem sizes used in previous studies. These results suggest high levels of maturity for Dpc on purely memory bandwidth-bound kernels. SYCL results are shown on the bottom right chart. The commit leading up to the 0.9 release during January 2021 saw the addition of the new Boost Fiber-based scheduler for SYCL's OpenMP backend. We see an encouraging performance uplift following those commits on the CPU platform. Performance for the CUDA backend seems to have reached maturity, with the results showing higher than 90% of the peak bandwidth, similar to GPU results from Compute CPP and Dpc++. Finally, we also did a comparison between SYCL implementations using the latest version of each compiler compared to the latest publicly available versions of alternative frameworks. The bandwidth achieved on each platform are in line with existing literature. As expected, the performance profile of SYCL implementations that depended on Intel's OpenCL runtime is very similar to OpenCL's, which share the same runtime environment. Given the higher abstraction level, it is encouraging to see performance parity with OpenCL, which focuses more on exposing lower-level controls. It is notable that SYCL showed highly competitive performance compared to the vendor-specific APIs like CUDA. We attribute SYCL's lower performance on AMD Rome to LLVM10's immaturity on the Zen 2 architecture. As later revisions of SYCL supports more up-to-date versions of LLVM, future versions of the study will attempt to accommodate for this. Our second benchmark is a compute-bound benchmark called BEAUD. The Bristol University Docking Engine, or BEAUD, is a molecular dynamics application that simulates the docking of different molecules to predict the structure of the resulting complex. The figure on the right illustrates visually the docking of a ligand, a drug molecule, to the receptor. MiniBEAUD is a proxy application that implements the computationally intensive virtual screening process of the full BEAUD application. The mini app has been renamed to MiniBEAUD for differentiation between the full BEAUD application. This change occurred after the submission of the full paper, where we still use the BEAUD name to refer to the mini app. For MiniBEAUD, The main and only kernel computes a set of transformations from a list of molecular poses which are then applied to the Cartesian product of all possible ligand and protein combinations. To complete the screening process, we compute the energy for each ligand and protein combination, which involves heavy use of single precision square root, absolute value, and general arithmetic operations in a tight loop. The use of hierarchical parallelism has been avoided for Bude. All kernel invocations use plain cyclical parallel for-calls. This was done to avoid scheduling issues as frequently observed in OpenCL programs when run on the CPU. Please see the full paper for detailed algorithm breakdown and selected benchmark configurations. Here we present results for the compute-bound Bude mini app. Compute CPP results are shown on the bottom left chart. We see a series of performance regressions with performance impact of up to 20% spanning nearly a year, starting in January 2020 with version 1.2.0 and only fixed after the release of 2.2.1 in October 2020. One potential cause of this is the transition of Compute CPP to LLVM7 in version 1.2.0 and then to LLVM8 in version 1.3.0 as described in Compute CPP's release notes. The two versions that carry the regression, version 2.0.0 and 2.1.0, mainly focus on SYCL 2020 implementations such as USM, shedding light on why the performance regression persisted for so long. It is also interesting to see results on AMD outperform Intel by up to 20%, almost consistently, given that Compute CPP runs on Intel's OpenCL runtime. In part, this may reflect the challenge of efficiently exploiting the wider vectors on the latest Intel platforms, 512-bit, compared to the latest AMD platforms, which maxes out at 256-bit. Dpc Plus results are shown on the bottom center chart. You observe a small improvements on AMD platform, but minor regressions on Intel platforms from the nightly build in mid-August 2020 onwards. The release notes point to the addition of dead argument elimination optimizations which were added during that time. Impressively, the SYCL version of Bude achieved nearly 40% of single peak precision floating point on AMD's Rome CPU when using the Intel Dpc Plus SYCL implementation. It is highly competitive compared to alternative frameworks as shown on the top right chart. SYCL results are shown on the bottom right chart. Performance for Bude on SYCL has remained low throughout all benchmark runs. This result suggests poor interaction between LLVM's OpenMP backend and SYCL itself. Performance for the NVIDIA GPU is much better, however, achieving 20% of VIA100's peak single precision floating point capability. As with BabelStream, we also compare the results to alternative frameworks. Performance disparity on Intel's Cascade Lake and AMD Rome suggests room for improvements for compute-bound operations. In particular, SYCL performed very poorly compared to the OpenMP implementation. This is surprising and requires deeper analysis on the emitted code. Results from OpenCL are also surprising as implementation share the same runtime for Dpc Plus and Compute CPP. Considering Bude's OpenCL kernel versus the SYCL kernel, which is nearly identical, this disparity likely originates from the code emitted by Intel's OpenCL runtime online compiler. This isn't a problem for Dpc Plus or Compute CPP because SPIR instructions are generated ahead of time. Our final mini app is a mixed memory bandwidth bound application called Cleverleaf. Cleverleaf is a performance proxy application for computing 2D hydrodynamics via the compressible Euler equations. The mini app implements the equation via a second-order accurate method which makes use of structured grid on the Cartesian plane along with a set of compute kernels that traverses this grid. Like most structured grid codes, Cleverleaf is a memory-bound mini app. Most of the kernels are fairly simple, involving few built-in math function calls on a large slice of the 2D grid. There are two kernels that require non-trivial reductions of multiple values. Cleverleaf has a characteristically high kernel count, where most of them are invoked in a tight loop. This is representative of typical HPC applications, which allows us to compare kernel scheduling overheads. See the full paper for detailed algorithm breakdown and select the benchmark configurations. Here we present results for the mixed memory bandwidth bound Cleverleaf mini app. Compute CPP results are shown on the bottom left chart. Compute CPP showed a significant improvements in runtime on CPUs, up to an 80% improvements from Cascade Lake and 34% for Rome. Cleverleaf's built-in kernel profiler show uniform improvements across all compute kernels. The improvements are proportionate to the overall reduction in runtime. As Cleverleaf's kernel are all unique and covers both iterations and reductions, the improvements observed here should be universally applicable. Dpc Plus results are shown on the bottom center chart. We again see a consistent runtime across all versions of Dpc for all supported platforms. This is within expectation as both Babelstream and Cleverleaf are both memory bandwidth bound. SYCL results are shown on the bottom right chart. The commit leading up to the 0.9 release saw the addition of the new Boost Fiber-based scheduler for SYCL's OpenMP backend. We see an encouraging performance uplift following those commits on CPU platforms. Performance for the CUDA backend seems to have reached maturity, with the results showing higher than 90% of the peak bandwidth. We did find a memory access bug on the 0.9 release which produces results that do not pass Cleverleaf's verification. A bug was filed and promptly resolved. The bug fix has made it into the 0.9.1 release. As with Babelstream, we have compared the results to the alternative frameworks. Initial analysis suggests SYCL has a relatively high kernel invocation overhead on CUDA platforms. This is less obvious in both Babelstream and Butte, as both only invoke a single kernel with no complex kernel dependencies at runtime, and also at a much lower frequency. On the other hand, Cleverleaf contains more than 170 unique kernels with complex dependencies, which is called a tight loop for up to 3,000 iterations. OpenCL once again performed poorly. We observe a 25% regression for SYCL implementations hosted on the same runtime. SYCL results are closer to what we previously observed in Babelstream, although with a further 20 to 40% regression. Based on Cleverleaf's built-in profiling data, we suspect the regression again stems from kernel overhead, which is amplified by the amount of complex buffer dependencies between each kernel. This study has found that all major SYCL implementations are approaching maturity from incremental performance improvements made throughout the last few years. The two vendor-backed SYCL implementations, Dpc and Compute CPP, both showed competitive performance compared to alternative frameworks such as OpenMP and OpenCL. Open source implementations such as SYCL also showed competitive performance for memory bandwidth bound applications. Recent releases of SYCL has put an emphasis on further reducing kernel overheads. We have seen strong evidence in improved platform support as shown in Dpc commit history where CUDA is in the pipeline. We hope this study contributes to the improved stability and robustness of all SYCL implementations. The many apps presented in this paper could serve as a viable baseline for SYCL regression detection, both in performance and general usability. Based on the findings with Butte, we also expect further optimizations on compute-bound applications. Overall, we conclude that, given the relative maturity of the three SYCL implementations, potential adopters of SYCL can now start to seriously consider it as an option.